The purpose of this slide is to talk about Nullstellensatz. So we will give 5 versions of Nullstellensatz. These are taken from Ravi Vakil's notes. So let us start. So first I want to fix a ring A. Here this is just a polynomial ring. So it is a K algebra of finite type where K is closed. So version 1. So version 1 of Nullstellensatz. So suppose you have polynomials f1 to fm lying in the ring A, and these polynomials generate, you form these polynomials generate an ideal. Yeah, so that's why I'm writing it as brackets, and this ideal is not the unit of the ring. So these polynomials do not generate the entire ring A. Then the system of equations f1 equals to 0, f2 equals to 0, fm equals to 0. So this system of equations has a solution. So you can say this solution is, you can say either it is a tuple in Kn, or just you say that there is a solution set in K. So you anyway will have solution, means there is at least has to be one point, say a1, a2, a3 for each x1 to xn. So you can say either solution in K or solution in Kn. So yeah, so basically it says you have a bunch of polynomials. These polynomials do not generate a unit, then they have a solution. Now an immediate consequence of this, or a version of this, is that suppose you have a maximal ideal M of ring A. So this is a maximal ideal, then obviously it does not generate 1. Then this maximal ideal is of this form. Yeah, x minus x1 minus a1, x2 minus a2 to xn minus an. Yeah, I'm writing x minus, I should write x1 minus a1, x2 minus a2, xn minus an. And then you have, this is the solution. Yeah, so you can say this is just a one tuple in Kn, or you can say these are elements of K, just like in above. So version 2 is nothing but a consequence of version 1. So now we come to version 3. So suppose I is a proper ideal in this ring A, then variety of I is non-empty. So this is a proper ideal, and then variety of I, or vanishing set of I, when you write V of I, it is non-empty. Notice that we have to have K closed, because there is a counter example. For example, if you take ring R, then x square plus 1 is a proper ideal of ring Rx. But as you can see, the variety of, or vanishing set of x square plus 1 is just the null set, because you obviously do not have complex numbers in R. So version 4 is, this is the most often quoted one. So let I be an ideal in this ring A. Then you have this correspondence. I, ideal of the vanishing set of I, is equal to the radical of I. So if you do not know what a radical ideal is, then you should stop here, see the definition in Wikipedia, and come back. So the idea is this, that there is one-to-one correspondence between radical ideals and algebraic sets. So if I is itself a radical ideal, that is I is equal to root I, then there is one-to-one correspondence between algebraic sets and the radical ideals. Now we come to version 5, whose proof we will write on this slide. So you take a bunch of polynomials f1 to fr and then g in ring A. and these are all polynomials in ring A, and this G is 0 or G vanishes whenever F1, F2 to Fr vanish. So that means that G is 0 whenever F1 is 0, F2 is 0, all the way to Fr is 0. So let us write this down. So in that case, if this is true, these are all G is 0 whenever F1 to Fr vanish, or G vanishes when F1 to Fr vanish, then we have this equation. That is Gn is equal to this A1 F1, where A1 belongs to ring A, then A2 F2 all the way to AR FR, and AR belongs to ring A. So each of these AIs belongs to ring A. So in other words, Gn lies in the ideal generated by F1 to Fr. So let us write the proof of this. So the case G equals to 0 is obvious. Obviously if G is 0, it vanishes anyway. So when all these F's vanishes. So there is almost nothing to say here. So assume G is not 0 and you introduce a new variable T. So you introduce a new variable T. Then you consider the following polynomials. Again we have this F1 to Fr and G, these are already given to us in A, and you also have this new polynomial Tg minus 1. So Tg minus 1 is an element of At. So yeah, so you just have adjoined T to the previous ring. Now notice that this is very important. This does not have a common solution in this closed field K. So why is that? So either if all the F's vanishes and G vanishes, then Tg minus 1 would not vanish. And that is precisely the point. Tg minus 1 does not vanish. That is the obstruction. And therefore you do not have a common solution. So what you do is now, by version 1, since these polynomials do not vanish, so now we use contrapositive of version 1. So if the polynomials do not vanish, then they have to generate the entire ring A, or they have to generate 1. It is equivalent. So if they have to generate 1, then we have to write it like this: P1 F1, P2 F2, Pm Fm. So yeah, so this is now we are writing these polynomials are generating 1. So now set T equals to 1 by G in the formula. And you notice that Pi and Q are all elements of At. So now what you want to do is you set T equals to 1 by G. Now if you do so, then you have a lot of this, all these P1s will have some denominators, and the denominators will be precisely in terms of G. So say P1 has G2, P2 has G5, Pm has G10 in the denominator. So you have this finite number of terms, so you multiply with a large enough n so the denominators cancel out. So if you multiply with large Gn, now this is precisely because the Pi and Q, they are both polynomials in At, so they have denominators when you replace T with 1 by G. So you clear these denominators out by multiplying with the large value of Gn. And then you know that left hand side now becomes, since Tg minus 1 will now become 0 when you put T equals to 1 by G. So the left hand side now is nothing but generated by the polynomials f1 to fm, and right hand side is gn. So right hand side is, now after you have multiplied with gn, so right hand side you can say gn is generated by f1 to fm, or instead of right hand side I should say left hand side essentially here, which I have underlined, is now generated by f1 to fm. So p1 f1 p2 f2 is nothing, all the way to pm fm is nothing but the ideal generated by f1 to fm, and right hand side is gn. So let me correct this. So left hand side, which I have underlined, is generated by f1 to fm, and right hand side, when you multiply 1 by gn, you get gn. So I'm just underlining it. So on this slide we would like to record the proof of Nullstellensatz version 1. So before we write the proof of version 1, we have to first prove a lemma. So if we have the system f1 is 0, f2 is 0, all the way to fm is 0, with each fi belonging to the ring A, as you know in the previous slide we defined A as k, then x1 comma x2 all the way to xn. Yeah, so this we have already defined. So k, then square bracket x1 comma x2 all the way to xn. So if this thing, the system of equations has a solution in some finitely generated extension field k of the small k, yeah, the small k is algebraically closed and k is a finitely generated extension field, then we have a solution in this smaller field k. So what we are saying is that if there is a system of equations and it has a solution in a finitely generated extension of a field which is a closed field, then it will also have solution in the closed field, in the smaller field. So if you have solution in the larger field, you will have the solution in the smaller field if the larger field is a finitely generated extension. The first thing is that what are finitely generated extensions? So the finitely generated extensions look like this. So you have bunch of elements t1 to tr. These are algebraically independent over this closed field k, and then you have theta, which is the root of a polynomial. So this is what a finitely generated extension looks like. Yeah, so this is the result which we will be using. So this is how finitely generated extension looks like. So since we are saying theta is a root of a polynomial, we have to write some polynomial now, and obviously this polynomial would be irreducible. So we are writing p capital T comma u, but capital T is nothing but it is, I'm just skipping t1 t2 all the way to tr and writing, instead of writing that entire r tuple, I'm just writing capital T, and u is some variable. So we just write a polynomial like this. So you have some polynomial like this, a polynomial of degree n. So the coefficients, these a0t and a1t, a2t, these are all nothing but polynomials in this here. You have t here. Yeah, so I should mention again, yeah, so the t is so it's something like this. Now I'm writing it in a square bracket, but you can also write the first part T1 to TR in round brackets, meaning that K round bracket T1 to TR, because it could also be the coefficients could also be that A0 could also be fractions, yeah, and then theta in the square bracket. So now we are talking about a solution. So suppose there is some solution of the polynomial equations, and where each of this solution belongs to capital K. I'm writing small k here, that is wrong, it should be capital K. Each solution belongs to capital K, that is a larger field. So now we can write this solution, since it belongs to the larger field K, we can write something like this: Ci t comma theta, where t is all T1 to TR. Again, I should have written yeah, no, that is fine. So that is pretty much it. So again, this solution belongs to the solution of the irreducible polynomial, and this solution Si belongs to capital K. So we have the system. So this is also the system of the solution. So we will have something like this for each for f1, f2 to fm, or for in general for fj, we have this solution. You put these n tuples or r tuples in. So yeah, so you put this. So you have field A, since fi belongs to A, where A is k square bracket x1 to xn. So this polynomial has n terms in it. So this is the solution. So it has to be equal to, because P is a irreducible polynomial, so you divide by the irreducible polynomial and you get this. Yeah, so since S is solution of both left hand side and right hand side, you see there is no remainder. And this Qj is some other polynomial. Now what we want to do is, we want to substitute xi, say xi which was coming from A. So we want to substitute xi with alpha I. Notice that A was k x1 to xn. So we want to substitute whatever x's you have anywhere which are existing in fj, you want to substitute them with alpha I, which belongs to this small k. Now what values of alpha we should choose, alpha 1 to alpha n, because each x1, x2, xn has to be substituted with alpha 1, alpha 2, alpha n. So what should be the values which we should assign for alpha 1 to alpha n? So the values which we assign are precisely those values, so that the denominators in any of the coefficients. So notice that I said that in this polynomial P, there could be some fractions and denominators, because each of the coefficients a0t, a1t, a2t, these could be polynomials or fractions. Yeah, I have written it as a polynomial, but these coefficients could be fractions. So we want to make sure that those AIs as well as these CIs or these QJs, their denominators should not become 0. And since we have finite of these, we can always choose alpha 1 to alpha n such that the denominators do not become 0. So our life is easy. And similarly, we do not want the leading coefficient of the polynomial to be 0, because that will cause problems with the irreducibility. So we choose u equals to tau to be one of the roots of the polynomial. Once you replace all x1 with alpha 1, x2 with alpha 2, xn with alpha n, then you can find the root of the irreducible polynomial p and let the root be tau. So then you have this is equal to 0. Now you simply do is this, you set this Ci or Cj, which I have underlined with yellow. So just set this Ci or Cj with the with alpha 1, alpha 2, alpha 3 all the way to alpha n, and then tau as, then you put tau as lambda j for all j, or lambda I for all I. Now notice that this lambda now lies in the smaller field K. And that is pretty much it. Now you have found all these lambdas. For each C1 you can find a lambda 1, C2 you can find a lambda 2, C3 you can find lambda 3, and all these lambdas essentially lie in the small field K. You just find it by substitution. So basically, because you chose all these alphas to be in small field K, and then the root will also come out to be in the small field K. Yeah, because the field K is closed. So thus you have a system of solutions. Yeah, so for every fj you can have lambda 1, lambda 2, lambda n, which will give you 0. So the only thing to notice is that in the proof is you need to know the algebraically independent structure. You fix the root of the polynomial, you find an irreducible polynomial with some coefficients which are in a field, and clear the denominators, and you get the result. So now we want to write the proof of version 1. So if the ideal, this f1 to fm, is not the entire ring, so this is not the entire ring, that is, this ideal does not generate 1, then it is contained in some maximal ideal. So if it is contained in some maximal ideal, we will construct a field out of it. Yeah, so this is A over M, where A is again k x1 to xn modulo m, and each xi, the image of xi, so you take this xi in A and you map it to Si. Yeah, so this Si is precisely what Si we had in the proof above. Yeah, so K, now you can write K as S1 to Sn, yeah, because Xi gets mapped to Si and K is a field. So by the previous lemma, the lemma above, this S1 to Sn is the solution of the, so this S1 to Sn, by after some modification by using alpha and converting it to lambda, will give you a solution in the ground field small k, and that is the end of the story. So this slide is extremely important. It basically captures the essence of Nullstellensatz and what it is useful for. So again, this is corollary. You can find this in Claus-Heulich's algebraic geometry, page 24. So you fix the ring A, yeah, and you have this ground field small k, which is algebraically closed, like we have done before. And you have these two maps, the vanishing set map V and the ideal I. So we have already seen this correspondence between ideals in ring A and subsets of the affine n space. So let us write this down. And we have the following bijections. So radical ideals of A, and all these are consequences of Nullstellensatz. So you have radical ideals of A. So these are in one-to-one correspondence with the subvarieties. Now, these radical ideals contain prime ideals, which are in one-to-one correspondence with the irreducible subvarieties of the affine space. This we will show separately. So prime ideals are in one-to-one correspondence with irreducible subvarieties. And the last is the maximal ideals of A. Obviously, maximal ideals are contained within prime ideals. These are in one-to-one correspondence with the points of affine space. And obviously points in affine space are contained within the irreducible subvarieties. On this slide we discuss some examples. On the previous slide we noted some consequences of Nullstellensatz, and let us recall some of them here. So there is a duality between algebraic sets and radical ideals, or we can say there is a one-to-one correspondence, as we said in the previous slide. So the simplest example was, we took 2 points and corresponding to it there was a maximal ideal. So we had a1, a2, and corresponding to it was the maximal ideal x1 minus a1 and x2 minus a2. So we are just going to repeat that here. Fix point AB here, and corresponding to it you have a maximal ideal x minus a comma y minus b. Now we want to understand union of these algebraic sets. So the simplest case to start with is, so first let me just write down arbitrarily. So what the union of two algebraic sets. So they corresponding to u1 corresponds to a radical ideal I1 and u2 corresponds to radical ideal I2. So you see radical ideals will be intersection. So what will be union of 2 points? Now 1, 0 corresponds to ideal say I1, which is y comma x minus 1, or you can say y minus 0 comma x minus 1, and you have to do intersection with y comma x plus 1. So this is what you get y square y multiplied by y, then y multiplied by x plus 1, and then x minus 1 times y and x minus 1 times x plus 1. Similarly, we can find the union of two sets like this. Yeah, so you find the ideal, and y equals to 2 has this ideal y minus 2, and then it has to be multiplied by x minus 1, and then y minus 2 has to be multiplied by y minus 1, precisely because 1, 1 corresponds to x minus 1 and y minus 1.